Okay, let's look at part B of example 3. Here we have the function y equals x cubed minus 1. And we want to know, is it 1 to 1, of course. Well, if we use the horizontal line test, we'll see that any horizontal line that you could imagine is only going to hit the graph in one place. Now right here it levels out for a moment, but it doesn't go like that, where a horizontal line would hit it in more than one place. So yes, this is a 1-to-1 function. All right, now you try it. Look at these 3 problems on page 283. Number 11, number 13, number 16. And number 13, I'll give you a hint. It might be easier for you if you just draw the graph or do the graph on your calculator. Okay, how did you make out? In number 11, we look at those ordered pairs, we see that 1 corresponds to 5, but 4 also corresponds to 5, so no, it is not a 1-to-1 function. In number 13, we have the function f of x equals quantity x minus 3 cubed. If you graph that function, you see you have this situation, very similar to this one. And all horizontal lines hit the graph in exactly one point. So yes, this is 1-to-1. And then in number 16, they give you the picture of a function. You don't know the equation of it, but you can see that any horizontal line that you imagine hits the graph in exactly one spot, so you're good. Of course, if it didn't hit it at all, that doesn't hurt either. That's still okay. As long as you do not have a horizontal line which hits the graph in more than one place, you're okay. It's 1-to-1. All right. Now, recall this diagram from a little bit earlier where we were introducing the idea of a 1-to-1 function. Notice that if you reversed all these arrows, what do you have? Another function. Right? No problems. These correspondences are all legal. It's a function. If you reverse all these arrows, what do you have? You have a problem. 8 corresponds to this output value and also corresponds to this output value. So this relation is not a function. And that tips us off to something in general. If a function has an inverse, well, if f is a function, its inverse is often denoted like that, f to the minus 1. Now, of course, it's not really an exponent that's acting on it. It's just notation that looks like exponential notation. But this just is read f inverse. So if f is a 1-to-1 function, this exists. And vice versa. If a function has an inverse, then that function is 1-to-1. So if f inverse exists for a given function f, then f is a 1-to-1 function. Let's look at example 4. Part A. The function f of x equals x cubed minus 1. And we're asked to determine if it has an inverse. Well, in example 3, we worked with this very same function, and we showed that it is a one-to-one function. Therefore, since it's one-to-one, it also has an inverse. Part B, this is a lot harder. Verify that g of x equals square root of x, cube root rather, of x plus 1 is that inverse. Okay, how would you do that? Well, you have to go back to your definition for inverse functions. If g is the inverse of f, and f is the inverse of g then, this has to be true. Right, I replace g of x with its definition here, and now f is the function that takes whatever you give it. In this case, I'm giving it the cube root of x plus 1. Takes whatever you give it, and it cubes it, and then it subtracts 1. The cube root of anything cubed is just that thing. So that gives us back x plus 1. And of course we have this minus 1 over here. The minus 1 and the plus 1 will cancel each other out. I get x. So it looks good. However, the job's not complete until you show the same thing happens this way. Let's take g of f of x. So we replace f of x by x cubed plus 1. And then we know that g is the function that takes the cube root of whatever you give it, with that it having 1 added to it. So we're feeding it x cubed minus 1, and we add 1 to that, and then take the cube root of the whole thing. Minus 1 plus 1 just gives me the x cubed. The cube root of x cubed is x, and I'm done. So what I have shown is that g of x is actually the inverse of f of x. And you notice I keep saying the inverse instead of an inverse, because there can't be more than one. It can be proved that the inverse function is unique. All right. Work this one out. Does f of x equals minus 2x squared plus x plus 1 have an inverse? Just yes or no. Think about that. Well, there's a quick way to answer this problem by using the horizontal line test. What does the graph of this function look like? Well, it's a quadratic function. There's an x squared term, an x term, a constant term. There's nothing illegal. So this is a parabola. In fact, since there's a negative number multiplying x squared, it's a parabola that opens downwards. Now, I don't know where it is. I just randomly drew it. But I know that since it's a parabola, it's easy to find a horizontal line that hits the curve in two places. So therefore, this is not a one-to-one function, and therefore it cannot have an inverse. Let's do example 5. This is a little harder. We're going to find an inverse. Sometimes that's not so easy to do. Example 5 on page 279. Part A. We're given a function f of x equals 2x minus 1 over 3. And we want to find its inverse. Make that a little more readable. First, let me just let y be equal to that function, f of x. So then, this is true. All right, just replacing f of x with y. Now, in your textbook, it shows you this nifty step. Switch the variables. Write x where y used to be, write y where x used to be. So they're just switching roles. So what's their relationship? Their relationship is reversed. We're going to make up the inverse here. We're going to reverse the process. Solve for y. Okay. Add 1 to each side. And where do I get? I arrive here. Y equals 3x plus 1 over 2. That, in fact, gives me my inverse function. F inverse of x, then, is equal to this. And in fact, a nicer way to write it is in slope-intercept form, if we wanted to graph it, and we do. All right, this is a line. There's your slope. There's your y-intercept. Okay. So in part B, we're asked to graph this original function and its inverse and see what the relationship is. Draw my coordinate system. And to draw f of x, let's put this in slope-intercept form. Now I see it's a line that goes through minus 1/2 on the y-axis. That's the y-intercept. The slope is 2/3. Now 45-degree angle going straight up is slope 1. So this is a little flatter than a 45-degree angle. So here's f of x. Now let's graph its inverse. Here, the y-intercept is at positive 1/2. The reverse of this. And the slope is 3 over 2. That's the inverse of 2/3. Is that coincidence? I don't think so. Slope of 2/3, still going up, but not as steep. Oops, I drew this one kind of poorly. Yeah, let's fix that. a slope of 3/2 is steeper. Okay, this is all right. Steeper than that 45-degree angle. So this is F inverse of x. Now, if you looked at that 45-degree angle itself, you see that. The inverse is the mirror image of the original function, and vice versa. Flipped around this 45-degree angle. And what's the equation of the 45-degree angle? Well, of course, it's the line y equals x. So this is a new kind of symmetry. My line's a little wobbly there, but you get the idea. We say that these graphs are symmetric about the line y equals x. Symmetric about y equals x. You just flip them over around that 45-degree angle and they land on each other. And why does that happen? Because every point here, if we had a point AB, its reverse point is on the graph of its inverse, right? After all, that's what an inverse says, right? If f of x makes A correspond to B, then f inverse makes B correspond to A. So all the ordered pairs are reversed. That's why you have this mirror image spinning around the 45-degree line defined by y equals x. For homework, first, finish looking at these concepts in MML. Go to the assignment 4.3 video, and there's just one animation in there, or a video. It's pretty good. Shows you a lot of this graphical stuff. And then on page 282, 1, 3, 7, 9, 17, 23 through 29 odd. Thanks.